Hey there, this is going to be part two of applications of differential equations. It's just a quick recap. In part one, we demonstrated how you could use separable differential equations to create the velocity or the position functions based off of acceleration due to gravity, where we start off with a differential equation. Well, in this video, what we're going to be doing is we're going to take a look at how we can apply those skills to create the position, velocity, or acceleration functions to then answer some questions in context of a problem. Now here it says we have a true story, and I use that term very loosely, about Daniel. That makes me think of my younger brother, and this ridiculous question very much makes me think of him and how he can identify, he'll think of the most ridiculous way of solving a problem and think that is the best approach. But anyway, so he's a conservative student, and in 2016 wanted to get a picture of President-elect Trump. It was a snowy day, and everybody was building all the stuff to get ready for the inauguration. And Daniel realized that he wasn't going to get close enough, so he decided to go to the top of the Washington Monument with a drone with a camera attached to it, and he wanted to fly the drone towards the White House or towards where the inauguration was taking place so that he could get his picture. But unfortunately, somehow, miraculously, he got to the outside of the Washington Monument and fell 558 feet to the ground. And it was a good thing that he was wearing his squirrel flying suit that day because he thinks it will be useful in construction where he's working in high areas. And I really think OSHA would have a problem with that. But anyway, this is what I kind of think. You know, here's Dan and his squirrel suit, and usually this is what I'm thinking about. Like when people jump out of airplanes, they have kind of fabric here between the arms and the legs that they can kind of stretch out and catch the air, and in between their legs they have more fabric that they use to kind of help them glide in the air as they're falling. So anyway, that's what I'm guessing Dan looks like. He decided that's the best thing to wear to go to a presidential inauguration and sit on the top of the Washington Monument somehow. Uh, maybe maybe whoever wrote this question just really liked Spider-Man or something and said, okay, well, yeah, we can all be on the outside of the Washington Monument. But anyway, uh, so now that we have the problem situation, we need to be able to answer some questions about it. So how many seconds elapsed before Daniel hit the ground? Now, because this is asking us to identify a value of time, that can be done essentially with velocity or position, because both of those typically are going to have the variable t to represent time. So what do we know? Well, we know in advance that, so we have the, you know, Washington Monument. Okay, ooh, I missed that line really bad. It's just, we have the Washington Monument. It kind of comes up, has a little triangular peak, and here's Dan at the top of it saying, hey, here I am, here's Dan. Okay. Uh, how many seconds did it take before he hit the ground? Well, we know that because he's up at the top of the tower, that his initial velocity would be 0. And we also know that his initial position is going to be at the top of the tower of 558 feet. So what this is, and we also know, if you need to, because we're talking about it in terms of feet, we know that gravity is going to be negative 32 feet per second squared. And I think that's about all the information that we know offhand. Okay. So because they're giving us some stuff about the or we're able to reason what the velocity is going to be initially of being 0. We know that the initial height is going to be 558. I think that a position function is going to be something that we can use pretty easily to determine what the time is going to be. Now, here you can really kind of bypass, if you really wanted to, the actual calculus. We understand that because we have negative 32 feet per second squared, that we could kind of start off by saying, well, oops, we have this position function, s of t. It should be negative 16 t squared. We know the initial velocity is 0. We know the initial position is 558. We could really just start off with that and solve for time from there. Um, but because we're talking about applications of differential equations, let me show you how we can use the calculus to kind of arrive at the same conclusion. So we're going to take our dv, why won't you write, will be equal to the negative 32t, uh, and we'll just write it out as we've already separated the variables. So instead of saying dv over dt is equal to negative 32, we'll just have it written out where we separated the variables already. So we take the integration of both sides, so I get v of t to be equal to negative 16 t squared plus our constant of, oh, my hand keeps hitting something, plus our constant of c. Well, we know that the, I'm sorry, not d, not v of t, that's going to be s of t because we're starting with, there we go, s of t. So there's our position function. So s of t would be equal to negative 16 t squared, and we know the initial velocity is 0 and the position function is 558, so we wind up with the same equation that we were able to kind of just reason our way to without having to do any calculus. But now either way, however you came up with the equation, now let's solve it and figure out, well, what would the time be? So I'm going to set the equation equal to 0. So I have 0 is equal to negative 16t squared plus 558. And we're going to solve this equation for t. So move the 16 to the left side. So it becomes positive 16t squared to be equal to 558. Divide by 16. And we will get I don't know because I didn't write the number down. I just wrote the final answer, 558 divided by 16 uh, gives us 34.875. And then I take the square root of both sides. And I'm only interested in the positive value of the square root because we're dealing with time. So if I take the square root of both sides, I'm going to get time to be approximately, let's change that from equal to approximately, because the square root of that 34.875 number is probably not going to be a nice decimal. So take approximately equal to, and that would be 5.906 seconds. So from the top of the Washington Monument, Dan fell 558 feet in just under 6 seconds. Now, with that velocity in feet per second, did Daniel, how fast was he going when he hit the ground? Okay, well, we have the velocity, or we have the initial velocity from the previous question. We know how long it took him to hit the ground. So in this case, v of t, the velocity is going to be the antiderivative of the acceleration. And again, this isn't strictly necessary. I'm just demonstrating the calculus because that's what we're doing. Because you should be able to recognize that, well, the velocity should just be negative 32 2t plus the initial velocity, which is 0. So this is really what we should wind up with. And when I take the antiderivative of the acceleration function, so I have negative 32 dt, and that would give us, when I take the antiderivative, negative 32t plus the constant. But again, we know the constant in this case, c, is the initial velocity, which is 0. So we have v of t to just be negative 32t. So that is our velocity function. Now we can use the velocity function and the time that we got from the last problem to see how fast was he going when he hit the ground. So I'll kind of do that in the space on the left here where I have a little bit more room to write. So we'll say v of 5.906. Now that number, 5.906, that is, I'm just writing that to abbreviate it. We save that number in our calculator. We use the saved number in our calculator to be equal to negative 32 times 5.906. And when you type that into your calculator using your saved number, you get negative 188.976 feet per second. So 188, almost 189 feet per second. That's pretty fast. Okay, so there's that one. And again, you really didn't need the calculus to get it started, but the calculus is, we're talking about calculus, so I'll show you where it came from. And now, taking the answer that we had from problem 2, we want to convert the velocity that we were talking about into miles per hour, because let's be honest, most of us are going to be more familiar, it's going to just make more sense to us if we think about it in miles per hour as opposed to feet per second. But anyway, this is not going to really require any calculus whatsoever. We're just doing unit conversions. So we started off with negative 188, and again, I'm saving this number, 0.976. We're saving that number in our calculator, and we have feet per 1 second. And we're going to multiply that by, we're just doing unit conversions. We have 3,600 seconds for 1 hour. And we need to, so that's going to allow us to convert the time, but now we have to convert the feet into miles. So in 1 mile, there is 5,280 feet. And so you can see very quickly what the units are going to do here. Oops. Sorry about that. I have no idea what I hit, but anyway, where are we at? The feet here and the feet here simplify to be 1. The seconds here and the seconds here simplify to be 1, leaving us our answer in terms of miles per hour. So when you multiply 3,600 to the velocity that we had, the almost negative 189, and you divide it by 5280, that will give you your answer in miles per hour to be approximately negative 128.847 miles per hour. So I'm not sure how Dan's squirrel suit really helped him out so much, because if you're traveling 128 miles per hour and you hit the ground, I don't think that there's going to be much left of you after that. But we're going to go ahead and pause this video here. There are still some questions to follow up with Dan and his escapades in Washington. We're going to go ahead and pause this video here, and we'll do one more video to finish it up. But until then, guys, thanks for watching. Take care.